Hello, my name is Ben, and today I'll be joined by my co-author, Wei. Our research project is titled TeethTap, Recognizing Discrete Teeth Gestures Using Motion and Acoustic Sensing on an Earpiece. The co-authors on this paper are Franklin, myself, Songlin, Feng, and Cheng. So the vast majority of input techniques for mobile devices demand the use of hands, or eyes, as an input source. This can be inconvenient in certain scenarios. For example, how could you reject a call on your smartwatch while carrying groceries? Or how could you turn up the volume on a podcast while washing your hands? Prior research has explored hands-free and eyes-free solutions, using wearable input devices which focus on tracking head movement, jaw movement, lip movement, teeth movement, and tongue movement. However, these approaches often require heavy instrumentation on the user, such as cameras or headsets, which could be socially unacceptable in everyday life. On the other hand, more minimalist approaches often have smaller gesture sets, which can limit possible use cases. So with TeethTap, we set out to create a device that requires minimal instrumentation, while at the same time detecting a rich gesture set. We did this by integrating both an IMU sensor and a contact microphone together into one lightweight, compact, 3D printed form factor. The IMU and microphone are positioned just behind or underneath the ear, right here. And we chose this position since it's out of the way and often occupied by other commonly accepted form factors like headphones or earphones. The whole system is also wireless. So what is our gesture set and how do we come up with it? Well, we started by identifying which teeth naturally make contact when sliding the jaw left to right or forwards or backwards, like this. And we settled on these 4 places of contact: front teeth, left canine, right canine, and then the back molars. Now, for each place of contact, front, back, left, and right, we employed 3 possible manners of contact: single tap, double tap, and hold. This approach was inspired by linguistic principles, where sounds in linguistics can be grouped by place of articulation and manner of articulation. Only now it's place of contact and manner of contact. Single tap is a quick tap and a release. Double tap is composed of 2 quick single taps followed by a release. Hold is a single tap with a delayed release. We also included a special back triple tap gesture as an activation gesture, which we'll describe in more detail later on. So in total, that makes for 13 gestures. In TeethTap, we applied a bandpass filter to do denoising and calculate the energy for data segmentation in our system pipeline. Because of our small training dataset, we chose SVM to do noise classification. For gesture classification, we used a KNN-based algorithm with the distance measurement of DTW, since DTW is well known for finding temporal patterns between time series datasets. For a user study, to evaluate the real-time gesture recognition performance and usability of TeethTap, we recruited 11 different participants. Our user study had 5 sessions: a practice session, which was designed to help the participant familiarize themselves with the gestures and testing system; a training session, the data collected in this session was used to train an ML model; and then 2 testing sessions where we provided real-time classification results to the participant. Lastly, we had a remounting session, and the purpose of remounting was to better understand how TeethTap would perform after taking off and putting back on the device using the same training model. This is a common user behavior in the real world. In each of the 5 sessions, participants were asked to perform each of the 13 gestures 5 times in a random order. In total, we collected 2,771 gesture instances in the training, testing, and remounting sessions.
We found that our participants reached an average accuracy of 19.9% within 1,382 total teeth gestures for 11 participants in the 2 testing sessions. We also found that confusion was more prevalent among similar gestures, such as single tap and holding gestures in the same place of contact. To understand whether having both earpieces is necessary and which gestures are less prone to errors, by only having sensors on one side, we further analyze the accuracy with left-only earpiece and right-only earpiece from the two testing sessions. What would the system perform using data from only one side? We found that the average accuracy dropped to 72.4% using only the left earpiece and to 74.8% using only the right one. We modified the system to ignore place of contact and only output manners of contact, double tap, single tap, and hold. By only having single-side earpiece, we found the average accuracy only dropped by 1.6% for left-only earpiece and 2.9% for right-only earpiece. We modified the system to ignore manners of contact and only output place of contact, front tap, back tap, left tap, and right tap. The accuracy dropped 16% with the left-only earpiece and 15.8% with the right-only earpiece. Therefore, we conclude that TeethTap is much better at distinguishing between manners of contact than place of contact with using data from just one side. In our study, we concluded a remounting session to analyze how taking off the device and then put it back on would affect accuracy. We found the average accuracy of recognized 13 gestures across 11 participants reached 85.3%, which dropped 5.6% before remounting. For recording manner gestures only, we found that the performance only dropped 3%. Therefore, we conclude that manner gestures are less influenced by remounting the device. We then conducted a short evaluation to explore whether back triple gesture could function as an activation gesture, such as "Hey Siri," to redact false positive consents. TeethTap successfully recognizing our activation gestures with a 99.1% accuracy. We decided this gesture to be natural to product yet easily recognizable for the purpose of testing under various real-world conditions, such as talking, walking, running, eating, or drinking. In total, we collected 71.5 minutes of data from 11 participants while they were actively roaming around, eating, drinking, and talking. Their false positive errors were triggered, and 23 false negative errors among the 133 gestures. In our daily lives, we may not need to recognize all 13 input gestures at the same time. In other words, a subset of the 13 gestures may be enough for many applications. For example, the task of navigating through audio or video contact could call for the following 5 gestures. The accuracy of the recognized those 5 gestures is 92.3%. The holding gesture could be applied to provide continuous input, such as changing the volume. In this application, only 2 gestures would be needed: left hold gesture to turn down the volume and right hold gesture to turn up the volume. The accuracy of recognizing those 2 gestures is 93.2%. Phone calls often comes at social inappropriate times. TeethTap could provide discrete gestures that are eyes-free and hands-free to operate a call with the following 2 gestures. The accuracy of recognizing those 2 gestures is 98.6%. In the current user study, we did not evaluate TeethTap's performance in recognizing gestures while the user is in motion. We could also try collecting large sets of training samples and using more advanced machine learning techniques. Furthermore, our participants were all 21 to 34 years old, means we are not sure how the system would perform on early age groups. Lastly, we want to explore integrating TeethTap into new form factors, such as headphones or glass forms. That's the end of our talk. Thank you.